Hello and welcome. My name is Kleise, and in this session we'll explore the essentials of sample preparation for X-ray fluorescence analysis, or XRF. Proper preparation is one of the most important factors in getting accurate and reliable data. In fact, the most analytical errors originate before the sample ever reaches the spectrometer. Today we walk through the key steps and decisions that minimize those errors and let you take full advantage of your XRF instruments. Let's start with the big picture. The complete analytical chain begins with sampling, continues through preparation, and ends with the measurements. The largest potential error usually comes from sampling and subsampling. The next biggest comes from preparation steps that we control in our laboratory. Instrument factors as calibration stability are generally a relatively small part of the total uncertainty. If we control the sampling and the preparation, we control almost all of the uncertainty. Good preparation gives us three things: homogeneity, freedom of contamination, and representativeness. Homogeneity means that every portion has the same content. Freedom of contamination means that our processes and tooling don't add any unwanted elements. Representativeness means the small portions that we analyze are truly representative of the bulk material. Now homogeneity. For powder samples, we typically rely on tools. The first is a swing mill, a high energetic grinder that pulverizes and mixes in one step. The second is the planetary or ball mill, which gives intense blending of the material that is already powdered. Keep in mind that the grinding vessels can introduce a contamination. Tungsten carbide vessels can add traces of tungstens and cobalt, while steel vessels may add iron. Zirconia vessels can add zirconium. Choose the vessel material that will not interfere with your element of interest and record the choice in your method. Sample mass also matters. A pressed pellets generally need around 10 grams to form a robust disc. A fused bead might need only about 0.6 to 1 gram. Whatever mass you choose, make sure it's truly representative of the whole. Use proper splitting, such as a rifle splitter or a rotary splitter, before grinding and again before taking test portions. With a homogeneous powder in hand, we usually follow one of two preparation routes: pressed pellets or fused beads. Pressed pellets are quick and economical. You mix the powder with a suitable binder and press it, typically at a high force, into a disc that is ready to be measured. Pellets are excellent for trace element work where mineralogy effects are limited. Fused beads go a step further. We mix the powder with a flux, fully oxidize the sample, and melt it to form a glass disc. The melt destroys the original mineralogy, eliminating mineralogical effects and giving superb accuracy to major and minor elements. The trade-offs are more steps, specialized equipment, and a bit more operator skill. As a rule of thumb, choose pellets for routine trace work and high throughput, and choose beads for comprehensive assays or difficult matrices. XRF isn't limited to solids. Liquids can be analyzed with equal ease when they are contained properly. We use sample cups, often P1 for smaller diameters and P2 for larger diameters, sealed with a thin film. The film choice is critical. Mylar, polypropylene, Kapton each have different chemical resistance and X-ray transmissions. Strongly alkaline solvent-rich liquids may attack certain films. A dense or thick film attenuates low-energy lines more strongly, while a thinner film transmits more but is mechanically weaker. Always check chemical resistance and consider the energies of the elements you care about. Sample layer thickness matters for liquids because they are a light matrix. Make sure that the filled cup is thick enough to be effectively infinitely thick for the energies of interest, so that the incident beam is adequately absorbed and the emitted fluorescence is stable and representative. Choosing the right film, thickness and composition helps you to achieve both safety and analytical performance. Plastic material can be prepared in a similar spirit. We shred or gyro mill the polymer and then use a hot press to mold a uniform disc. As with liquids, plastics are in low density, so pellet thickness is important. Very thin pellets can be partially transparent to the beam and underestimate concentrations. Aim for a few millimeters of thickness, confirm with a gauge, and use the press temperature that avoids degradation of the additives you may be analyzing. For solid metals, the focus is the surface. We need a flat, clean, oxide-free face that is placed squarely in the collimeter path. There are two common approaches. Abrasive sanding or grinding suits harder alloys, such as steels and nickel or cobalt alloys. Be consistent and use the same grid size for your standards and your unknowns, because changing grids changes the surface roughness and therefore the measured intensity. The second approach is facing or milling, which is often better for softer alloys, such as high copper materials, lead or zinc. Sanding soft materials can smear the surface, spreading softer faces over harder ones, and create a layer that is no longer a match of the bulk composition. A light mill cut removes the material cleanly and avoids that smearing. Whichever method you use, remove only what is necessary. Clean away debris and ensure that the sample seats firmly and flatly in the sample holder. Across every sample type, keep thickness and matrix effects in mind. Light matrices, such as liquids, plastics, and low-density powders, must be thick enough to absorb the incident beam and generate a stable fluorescence. Heavy matrices, such as metals and oxides, reach infinite thickness quickly, but rough or oxidized surfaces can still scatter and reduce that intensity. Always calibrate with standards that match both the matrix and the preparation route that you are using. To wrap up, we reduce uncertainty by focusing on sampling and preparation. We create homogeneity with the right mills and vessels that don't contaminate our samples. We choose between pressed pellets and fused beads based on our analytical goals. We select chemical compatible films for liquids and ensure adequate layer thickness. We hot press plastics to suitable thickness and prepare metal surfaces consistently, choosing sanding for harder alloys and milling for the softer ones. Master these fundamentals and your XRF system will deliver accurate and reproducible data day after day. If you have questions or would like to have hands-on support, please contact our specialist team at Malvern Panalytical. Thank you for watching and happy analyzing.